మెల్లగా ఉంది. చల్లగా ఎయిర్ కండిషన్ ఫీలింగ్స్ అలా ఉంటుంది. చల్లగా ఎయిర్ కండిషన్ ఫీలింగ్స్ అలా ఉంటుంది. చల్లగా ఎయిర్ కండిషన్ ఫీలింగ్స్ చల్లగా ఎయిర్ కండిషన్ ఫీలింగ్స్ ఆ పేపర్ పాస్ అవుతారని వాళ్ళు పాస్ పాస్ కాదు అంటే ఎయిర్ కండిషన్ అంటే Hello, 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 hello. Okay, so unsupervised, like clearly, as from a human point of view, you can see here, like there are like two groups are here. These are similar groups of similar characteristics. Similar groups of similar characteristics. So I hope my screen is visible. Hope my screen is visible. I'm sharing a PPT, so I hope my screen is visible. If not visible, just tell me. Yeah, I think it's visible here. So like here, this is a cluster. So in unsupervised learning, this cluster will be classified without any kind of. So initially there is no labeling. So based on the like the common characteristics, you can see this is a group and this is a group and this is a cluster that doesn't have any kind of common properties. It's just all over the place, scattered all around. So in this, we can classify these two groups here. So this could be anything. So this unsupervised learning is mostly used in numerical data sets where there is multi. Here, this is a two-dimensional. Two features are given here, so it could be multi-feature, more than like two feature, data. Then self-supervised learning. So self-supervised learning is mostly used. This example that I'm showing here is like a image enhancement example where we have an image and it uses here using self-supervised learning we can enhance the image by predicting what is supposed to be there, like by analyzing what is all around that particular place. It will just predict what is supposed to be there and it will just give that output. So it can be used for image enhancement where there is like a blur in a particular image. We can just use it to use this type of uh, techniques to enhance that image. Then reinforcement learning is kind of like it's it's like reward and punishment, that type of understanding. Like if there is no human involvement, there is a human involvement in the sense of the initial setup. Like when it's like a game, playing a game, if you go through the correct path, you'll get points. If you don't, then you'll have setbacks in the game. So that is what reinforcement learning is. Like what if it chooses the correct pathway, then it will be rewarded. That means it will try to choose the correct path always. So that is reinforcement learning. So there are also like models where people like large models where multiple of these, like some models like if you take like DeepSeek AI, they use both supervised and unsupervised, reinforcement learning and supervised learning. Supervised learning is used less and more reinforcement learning is used. That's why DeepSeek AI is much more less expensive than, also hardware wise, it's less expensive because they use older versions of the GPU, like compared to like OpenAI. So, but like OpenAI is mostly supervised learning with labeled data. So, fundamentals of machine learning. So we'll just you go through like CNN. What is CNN? Convolutional neural network. So CNN, this is an example. This is one of the most basic example of a CNN network, convolutional neural network, where the here this example is of number detection. This is a handwritten number detection where we have like numbers from 0 to 9, and these are handwritten numbers, and the input image is a binary image. So it's a binary image 28 by 28, one single channel image. It's a binary image, so it's single channel 28 by 28. That's the size of the image. So then here, so convolutional neural network means it just it gets the name convolutional neural network because mostly in this type of machine learning technique it uses convolution the mathematical operation of convolution uh, to convert the data, to extract the features from the data. Also, other things are used. Other mathematical operations are also used, like max pooling. But mostly it's just convolution. That's why it's called convolutional neural network. So here we can see this. There is a kernel. So a kernel is a filter. So it's a matrix. Basically, it's a matrix, a filter, a 5 by 5 filter that is lit over the so the model will slide the filter over the image one by one, like over the image. It will cover the complete image. So we know that when we do convolution, what we do, just multiply the values with the constants, and then we add them all up, and then at last you will get a single number. For a collection of, for a matrix, you will get a single number. So this filter is the constants. Filter, the kernel are the constants, and the pixel values are the actual values. So this gets multiplied with the filter values, gets the kernel values gets multiplied with the pixel values, and then at the end we will get a single value. So this operation is continued n1 times. This operation is continued n1 times. Sometimes the filters might be the same. So initially the filters are random because so if you take this from a training point of view, if you are starting to train the model, then at that time these filters will be random, everything the filters. So then there is this thing called weights values. So weights values is regarding each of these each of these neurons here. Every neuron will get a weight value. Based on the weight value, the neurons will fire. So that weights value and the kernel value, sometimes it is fixed, sometimes it is predefined. In some special cases, like like Gaussian blur, or some special cases, or like edge detection, or something like that, where in that case the kernel will be a fixed value, but otherwise the kernel will be random values, or could be also fixed values. So here the same operation is done n1 times, and it creates this 24 by 24 feature map, and it is an n1 channel feature map. So that's from a single channel image we'll get n1 channels here by repeating this operation. So again, max pooling is done. Max pooling means saying there is a kernel 2 by 2 kernel, and instead of doing convolution, it just picks the highest value in that matrix, and the output of that operation is saved to the next level. So this again creates a 12 by 12 feature map of n1 channels. Then again, that repeated convolution is 5 by 5 convolution is repeated. So this is what is basically like inside of a convolution neural network. This is very basic, one of the most basic convolution neural network. Like if we do like simple Arduino programming, what we do initially is like LED blinking. So if we take deep learning and CNN, this is like LED blinking for that. So this is like the one of the most basic type of networks here. So most modern networks have like hundreds of or even thousands of these type of layers. So we'll come to this overall this optimization under. I think you might have already gone through all these things like underfitting, generalization, regularization, all these things. Like models with lots of parameter can easily overfit. So overfitting means in general, I'll just explain. Overfitting means like it can only work with it only works with the if it only works with the training data. If we give new unknown like unseen samples, if it doesn't detect that, if it doesn't give the kind of output that we want, then that is called an overfit model. So that a overfit model is not any good for in any real world applications because it can only work inside the train data. So that means we need to avoid overfitting. So generalization is it's the quality of ML model is measured on new unseen samples. So it should be very general. The model should be general. So for that we can use regularization. So regularization uses different kind of methods are used for to prevent overfitting, like simplicity, sparsity, dropout, early stopping, other than doing adding more data. Other than adding more data, regularization can be done by doing this. So then deep learning, how deep learning works, how the training process works. So initially, like I said, there is a set of weights. So the main when we talk about model consists of two things mainly. Every deep learning model consists of two things mainly. One is the weights file. Weights file means like it could be like in separate depending on the framework. It could be there could be two files or there could be one file. So there are two components are there. One is the weights values. Weights values, like I said, each node, each neuron has its own weights value. So this weights value is what decides the quality of the neural network, the quality, the structure of the neural network, the quality, how accurate the model is. Everything is decided based on the weights value by adjusting the weights values. So these weights values and then the structure of the neural network. The structure of the neural network is what we have seen just how many convolutional layers are there, how many max pooling layers are there, how many fully connected layers are there. So how many different kind of kernels are used, so kernel size, everything is that is the structure of the network. So weights values, then structure of network. That's what we need to recreate the network. Like after training, once the process of training is over, we want to use it in a real world application. We want to use it in so we want to do inference with the model. When we want to do inference with the model, we need to recreate the network again. So to recreate the network again, two things that we need is the structure of the network. Structure means all the different kind of operations that has to be done layer by layer. So there is a input layer, then there are hidden layers, then output layer. All structure of all these three things. I mean, it's not like three things. It's just like the hidden layers are could be any number of layers. So these structure and then the weights values to initialize all the neurons in the layers. So these are the two things that we need. So that's what a model comprises of. When we talk about model, that's what a model is. So here, this is a process of training. So it talks about training like layers. What are layers? So we've been talking about layers. So what are layers? Input data and output input data, targets, loss function optimizer. We'll go through all this. So this is like a general structure. There is weights values. So initially these weights values are like random values. So if it is a mostly if we are starting from scratch, if it is a fresh model we are trying to train, then these weights values are random and these weights values are given to the layer. Then there is input like the image that we are just seeing. So these weights values are applied to the nodes, and then then there is an actual true target. So this is labeled data set. So this is supervised learning. That means we have labeled data set. True data is there. So the prediction, the input value, the prediction and the true data are compared using a loss function. So the loss function compares the prediction and the true data and computes a loss score. So then there is this component called optimizer. So optimizer is nothing but a like a gradient descent function. So one of the most popular optimizer function is gradient descent. So gradient descent you might have studied gradient descent in like college level. It is like to find the minimum of any function. So here the optimizer is a so the here the optimizer is a uh, optimizer is a gradient some function like gradient descent function that can find the minima. So why we need to find the minima? Because we need to decrease this number. This we because we need to decrease the difference between the prediction and the true data. So that's the idea here. The loss function will calculate the loss score. So we need to minimize the loss score. So the optimizer will work on the loss function uh, work on the loss function. Will try to reduce the loss score. How will it do that? By adjusting the weights values, updating the weights value. The optimizer will update the weights values, and again the loss function will calculate the loss score. Based on the loss score, the optimizer will again update the weight value. So this is called an epoch. This is called a training epoch. So this is
ఏసీ లేదా పెద్ద ఏసీ లేదా ఏ ఫ్యాన్లు ఏం చేయి ఇగో ఈ పక్క ఫ్యాన్లే ఆన్ అవ్వలేదు
so please, if you're not saying anything, please mute yourself. There's disturbance to others. Like if you're not saying anything, if you're not asking anything, please mute yourself. Otherwise, just if you want to ask anything, if you have some queries to ask, please just use chat. Okay. So the loss function calculates the loss score and the weight is applied. So this is called an epoch. So in a training process, this is an epoch. And an epoch means a single cyclic training process. So no model can be trained by using a single epoch. It need to go through like so many different epochs. So normally we can use like 100 epochs depending on the kind of model that you want to train. If you have so much data, you might want to increase the number of epochs, or it depends on so many different factors. So that's it. That's the whole process of training inference. Both in both cases, this is the same process. So I think you got an idea about all these things, layers. So this is just slides about those things again. Data processing, layers are data processing modules, many different layers are there. They're like densely connected, convolutional, recurrent, pooling, flattening, merging, normalization. These are all mathematical operations: pooling, flattening, merging, normalization, convolution. Then input one or more tensors. So these are called, always they're called as tensors. In our example, it was a single channel image, and output also could be one or more tensors. So like tensors are like, obviously, tensors are like vectors, multi-dimensional vectors. So usually have a state encoded as weights. So learned, initially random, and then it's learned.
ஏதாவது ஒரு கிளாஸ் ஏதாவது ஒரு டாபிக் வச்சு கிளாஸ்
Uh, so usually then when combined form a network, or a model. So when it combined to when both these things are combined, like the layers and the weights, like I said, a model is these two things, layers and weights. Layers means all the mathematics, the structure of the network. Weights means the values, the learned values, which is the main thing which decides the quality of the model. So features in deep learning. In deep learning, features are automatically learned rather than manually engineered. Convolutional neural networks extract hierarchical features, like low-level features are like edges, textures. These are like low-level features. Then there is mid-level features, shapes, parts of objects. These are like mid-level features. High-level features, complete objects like faces, cars, etc. So in each so like any CNN network, like we'll see techniques to improve feature detection. Filters. A filter is also called as kernel. It's a small matrix, just like I explained. So it purpose is to extract spatial features by performing low-level element-wise multiplication with the inputs. An example like edge detection using Sober or Gaussian filter. That's a filter. That's a fixed filter. There could be also random filters. Then this is the same thing that we've been talking about. What is a loss function? Quantity to be minimized. So the most important thing that the network, most important thing that network cares about is the loss value, the loss score to minimize the loss. So loss score is error value. So the most important thing is to minimize that value. There might also be other matrices you care about. Common tasks are standard loss functions, mean, square, error for regression, binary entropy for two-class classification, categorical cross entropy for multi-class classification. So these are like different loss functions. Then optimizers like stochastic gradient descent, momentum, and the variance could be like a different kind of. So this is like anatomy of a deep neural network, DNN, CNN network. So then there are like frameworks. Frameworks are like, so we've been talking about these things. So framework, what are framework? Why we need to use frameworks? Like we've been up to now, we've been talking about convolution, max pooling. So what are all these things? These are all like mathematical operations. So we don't want to write the everything from scratch, like each and every single multiplication operation, addition operation. We don't want to write all those convolution layers, everything from scratch. So what frameworks does is they actually tools for defining static or dynamic general purpose computational graphs. So like a graph like this, like xy plus 5y plus 5. So this is an equation. Here you can represent it like a graph like this. Add like multiply two values and add them. So like that you can represent it. So the same thing, what frameworks do is they have like they've created all these predefined predefined computational graphs, and also they automate things, automatic differentiation, like seamless CPU GPU switching usage, multi GPU usage, distributed. And Python, there is Python, and mostly it is in Python instead of C, C++, or much more harder. Most of them are open source. Almost all of them are open source. Most of the popular ones are like PyTorch, Cafe. Uh, so then we are going to discuss about this particular thing called architecture called YOLO V5. So the YOLO V5 architecture, it's one of the most popular deep learning architectures. YOLO divides image into grid systems, and each grid detects objects within itself. They can be used for real-time object detection based on data streams. They require very few computational resources. And object detection in general. So in object detection, there are two components are there. So the output is a prediction of, like, if you take an image, in that image, how many while training, we'll label the data in a single image there could be like multiple objects. So the output is bounding boxes, number of bounding boxes covering the object that we want to detect. So the prediction is always bounding boxes. So the head, so in a general object detector, there is backbone for pre-training and head for predicting the classes. The backbone can run on GPU, CPU. So the backbone is used for feature extraction, and then the head is used for prediction, object detection. So recent object detectors have some layers coordinate, collect feature maps, and it is between backbone and head. That's another thing. So there are like different versions of YOLO, YOLO V3, YOLO V4, YOLO V5. So they are like how the backbone, neck, and head structure and kind of loss functions used. So I'll share this. So it's not architecture like YOLO V5. It's not a single algorithm. It's combination of multiple things. Here. So then YOLO V5 is a single shot detector. It's a single shot detector, which means it performs object detection and classification in a single forward pass through the neural network. Uh, this makes it very efficient for real-time applications. Like early versions of YOLO, V5 uses anchor box clustering, predicting bounding box dimensions, anchor box. So anchor box clustering means using the true data, we can just predict how how the size of we can predict the size of the bounding box. YOLO V5 uses CPS CSP Bag5 3 as backbone architecture. This modified version of acronym, which is known for its efficiency in the effectiveness in feature extraction. So backbone is always used for feature extraction. Then using the features, it predict the head predicts and gives us the bounding boxes and different other things. Also, bounding boxes means it will just give the XY values, XY width values. So then other things that it will give is like class score, objectness score, bounding box, like coordinates obviously. So then application wise, I can just share you one application here. So we have made this like this small scale setup of a self-driving car. So it's a small robot. It's a small robot, but it acts like a lane following. So it is actually I've used it. I've trained the data. I can just show you the video and just share the video here. So I'll share the screen. It'll be easier. So I hope the video is visible here. So here, this is a video of the model that we have created. So this is like a road setup here. So it has like dotted lines and continuous lines. So this is just a normal road lane. So I took pictures of this and I've trained a custom model using YOLO V5. And this using this custom model, this robot car is actually moving using this custom model that I've created. So it detects the lanes and it moves forward. So this is not a big actual like a self-driving self-driving vehicle, but this is like an example, a small scale example of the same thing. So in real world application, it also uses the same kind of techniques. I've also used semantic segmentation here to like label these lines here. So how I've done is like this one is this here it will detect the lane based on the structure like right side is discontinuous lines and left side is continuous line. So based on that, it will just detect it and it will make turns based on that. So this is YOLO V5 application. I've done this using YOLO V5. So that's it. Like it will just continue to do the loop detecting. So this is like an example application of how we can use YOLO V5. So then yesterday we have completed with the we have talked about ROS and it's like we have covered the theoretical part like what is ROS, nodes and everything. So today we'll see a practical example of the same thing. So yesterday we've been talking about ROS in general. So today we'll just see a specific application. It's called a autonomous robot. So this is our autonomous robot platform actually, which we are actually developing our own autonomous electric vehicle, which will be releasing so very soon, and I can just give you an overview of that. So we'll just go with the rows. So this is like initially, I'll just show you the video first and then I'll explain it. So this is the robot that we have here. This is our like robotic lab setup. You can set up this. You can set up this in your college for research purposes. This is not like a fully. This you can add your like I'll explain in a second. I'll explain what is happening here. So this you can set up in your college, and you can students can add more to that same robot. So this actual robot is here. I can show you the video of its movement. So this is actual robot here. So it's a four-wheel drive. It's not a four-wheel drive, two-wheel drive robot with a steering here, and then there is a sensor. In on at the front there is a sensor. So the sensor is so this is the actual model here. So there is a sensor here. So this is it's a LiDAR sensor. So we have discussed about LiDARs yesterday. So this is a single beam LiDAR, a 2D LiDAR, which is used for mapping the environment, which is used for mapping the area. So right now in this video, what you're seeing is our office space, office floor. So I'm just using this robot and it's on its own. It's exploring the area, exploring the floor, and it's trying to create a map. So that's what we can see here in that visualization video. In the visualization video, that's what we can see here. So initially, it's trying to create a map here. So right now, I'm not controlling the robot or anything. So this is called RVIS. This view here, this viewer is here is called RVIS. So I'm running this in Ubuntu. So you can see this is Ubuntu operating system, and this is a screen record of that while I was running it. So here this is called this visualizer is called an R called RVis robot visualizer. It is a part component of robot operating system. It's most popularly used like visualizer. So here what is happening is here this the robot that you just seen in that video, that actual green color robot, which is creating the map. So the which is creating the map by just moving around by using the lidar here. So what is happening here? So I'll just share it using so it's called SLAM mapping. What you're observing in the video. So the robot is in SLAM or simultaneous localization and mapping exploration mode. It uses a 2D LiDAR like RP LiDAR A1, that is a specific model, and it uses this ROS package called G mapping. G mapping is used for creating the map, creating the map. Then there is another thing called frontier-based exploration algorithm, which is used for like the Gmap will create the map using the particle filter. It will do the SLAM part, so simultaneous localization and mapping part. But the exploration part, where to go, so automatically the robot is creating creating its own goals and it's moving. Like you can see in the video, as the robot is moving, you can see as the robot is moving, there is this line you can see, it's like creating a path. Now the path has changed, so it's moving in reverse. So this green color thing is a velocity vector which is supposed to follow, the velocity vector. Velocity vector means it will just give the green color. There is so two distinct lines are there. One green line and then there is a blue line. Blue line is the path it's supposed to follow. Then the green one is the velocity vector it is supposed to follow. So the velocity vector means it will just give the direction and the direction in which way and how much fast it should move. So this is initially just creating a static map. Initially creating a map. So this is what happening. So it uses using G mapping and frontier-based exploration algorithm that commands the robot to move toward unmapped areas. So in this image, so this gray part is unmapped area and the white part is the empty floor, and the black denotes the boundaries. Boundaries means these are walls and different objects. So these are boundaries where where the robot is not supposed to go because it will collide with something. Then these green dots are laser points, which is used by the which is done through the done by using the 2D LiDAR. Then core functionality is building a 2D occupancy. What is the use of GMAP? Building a 2D occupancy grid map. So this is a grid map. This is a grid map, occupancy grid map of the environment using laser scans, estimates robot pose. Pose means position orientation, like position and orientation means X, Y plus. So this is a 2D map. So that means pose of the robot just means X, Y, and theta. Theta is the angle at which the robot is declined, like inclined or whatever. Position and orientation using odometry and scan matching. Then uses particle filter to track the multiple possible poses. So the particle filter is a probability-based localization algorithm. So like underlying data processing, what is happening, sensor input, robot collects laser scans from the 2D LiDAR, then wheel odometry. The wheels have inbuilt encoders that can, like quadrature encoders that can detect the direction of rotation, also count the number of rotations. So we can calculate the speed of the robot and in which direction it is moving. And we will just fuse that with the laser scans, and also we can use IMU. IMU is more redundancy in case if the floor is slippery, then wheels might rotate, but the robot might not move or turn. Uh, but that might register as a wrong, it might give a wrong pose information. So that can be prevented by adding an IMU sensor. Scan matching. The incoming laser scan is matched with the current map to estimate how the robot has moved. Then particle filters, multiple hypothesis particles are maintained, each with its own pose and map. Particles are weighted based on how well they explain the current scan. So based on that, one of the alternatives are chosen for localization. Map update. The best weighted particle map is updated with the new scan over time. A consistent occupancy grid map emerges. Then how the robot explores. It uses frontier detection, finds the boundaries between known map and unknown areas. Goal selection chooses the frontier points as next goal. Just automatically moves around, randomly just moves around the place. Then there is this thing called navigation stack, which uses move stack to send velocity commands to reach the goal while avoiding obstacles. So there is like, so these are all different nodes. So yesterday we talked about nodes. So this like frontier detection will be a node, and this navigation stack will be a node, and the G mapping part will be a node. So everything will, and the LiDAR will be a node. So everything will be a node. And what we have seen in that image, what you have seen, like green dots, what the green dots means, what the gray means. I've already explained all that. I'll share the PPT too, so you can just go through it. Then these are like different common ROS nodes and topics in use. Like SLAM G mapping, TF tracks SLAM process using particle filters, tracks transforms between maps and all of base link, localization only. AMCL, if like initially G mapping will create a map, will create a static map. Then using AMCL means uh, AMCL means adaptive Monte Carlo localization. So it's a localization technique, but it's not like G mapping it's not like G mapping, because for AMCL there need to be already a map should be there. Like we initially will use G mapping to create a static map, a global map, and then using that already saved predefined map, we'll use AMCL to localize the robot. So in actual SLAM, which we'll see in a second, actual SLAM, like the robot moving with the made map, like used once the map is built. So the initial, what we have just seen in the video is the initial process, building of the map. Okay. Then move base, path planning, velocity control, everything is done by using move base node. Then scan, publishes the laser scans, map, outputs, occupancy grid being built. So like summary of what happened. So then I'll just show you the video and we'll just wind up the session. So this is the second video here. Second video here. So in the second video, this is actually the first video itself. You can see mapping. So I've done mapping here. I've created a map, a complete map here. So I've saved the map using the maps server node. And then I'm going to run self-driving autonomous navigation. So here the robot is going to move on its own. So I'm going to give the goal location as this place. This is my goal location. So here, I'll explain this. This is a floor of our office. These are different cubicles, and this is a cabin here. So robot is at the one corner of the floor, and the goal location is going to be here. So it needs to move all the way from here to here on its own. So you can see this thing that moving around. There is a line. I think the line is yellow line. It's not that visible because it's white background and yellow, so it's not very visible, but there is a yellow line here. That is the actual path. And then there is this thing that moving around. So there is a velocity vector which is telling the robot which direction to move and how fast it is supposed to move. So now it will just try, it will go straight, and so to avoid collision, it will just take reverse, and then it will move forward, and it will just reach the position. So I can just show you the actual video of the same thing. I think this is on. So it's moving around. So you can see it's the same place that turning. So you can see it's going forward straight. Now it's a little bit confused, so it just takes reverse, like we've seen in that ROS, and then it will continue on the path. So it will always find the shortest path. That's why it's sticking to one side. So right now it is just going into that cabin, and it's going to stop there. Yeah, so right now it reached the goal location. Reached the goal location, so it stops there. So this is the actual output. Like if you use like robot operating system and all these sensors, and main objective of the robot operating system is to integrate all this cluster of all these things, like all these software parts, hardware parts, everything, bring everything together and make something like this. So you also use this in like autonomous cars, self-driving cars also, same technique. This one is a scaled model. The same ideology is applied to that one also. Okay. So I think the attendance link is already posted. You can just fill that. So this is the end of the session, end of the 5-day program. So I hope it was helpful. So that I've only, I've only led the session yesterday and today. So I hope the 2 days were helpful for you. So this is not like an in-depth into anything. This is just a start. You can just use these terms, and you can just use this as a beginning and start to like research on these things and start learning on these things. So we can provide like we can provide assistance on that also. You can contact us. We can provide assistance. We can set up labs so as far as ROS is concerned, it's always in research mode. It's never ending. Like same robot that I've shown, I can add more things to that. I can add GPS. It is like a very basic setup, that green color robot. I can add more things. So the students, once you buy something like that from us or someone else, whatever it is, you can just ask the students to integrate more sensors and more things into it, so they can so they can use it as a learning experience. So so thank you everyone. So again, once again, thank you everyone. So I'll just wind up the session here.